This week in 241, we'll be talking about data analysis. Why do we bother doing data analysis? If you have a large amount of data, your audience does not want to sift through all of it to figure out what it means. You need to condense that data for them so that it conveys the necessary information to your audience at a glance. Let's use an example. In honor of Selection Sunday, let's look at Tim Hardaway Jr.'s stats and ask how many points will Tim Hardaway score in his next game. While I made this presentation on Saturday, I did not do the audio and put it online until after the game was already played. So this example will be predicting how many points he scored on Sunday. If you look at Tim Hardaway's stats on ESPN's website, you can see how many points he's scored in every game that he's played this season. The list goes on and on. To the casual observer, this is nothing but a bunch of numbers. Is there any information that we can draw from the points scored? If you go to the Wolverines main page, you'll see that there's only one number that they report for Tim Hardaway, which they call the points per game. This number is the mean, or the average of the data. It is found by summing up the total number of points that were scored and dividing it by the total number of games that were played. For this example, I'll just use 5 games. We can write this in more general terms. Let's give the points scored on the different game days different variable names. So x1 for the points scored during the first game listed, etc. The total number of data points, which is the total number of games played in this case, is n. I can then write the mean just using variables. Replace the sum with a summation symbol and you have the equation presented to you in the manual. Does the mean provide you with enough information to get a good sense of the data? By looking at this mean, you might get the impression that he always scores around 15 points every game. But in reality, the points he scores in a given game can vary quite a bit, like when he got lucky on Thursday when he played against my alma mater. We need to take the spread of the data into account. We can look at the spread in the data by plotting a histogram. I'm going to make a mark for each value that lies between a given 2 values along the x-axis. So for instance, for 25, it happens to be one of the x values specified along the x-axis. So I'm going to make a mark just to the right of that 25. I do the same thing with 10. 14 lies in the 10 to 14 range, so I put a mark there. Note that there's already a mark there, so I just place it on top of the other one. Filling in the rest of the values, I now have my histogram. With this histogram, I can see at a glance that during 3 games, he scored between 10 and 14 points, while he only had 1 game in which he scored between 25 and 29 points. It seems that chances are he's more likely to score between 10 and 14 points during Sunday's game. We also have a statistic for this spread called the standard deviation. Once again, we use our 5-game example and plug the numbers into the equation that was presented to you in your manuals. Note the game where he scored 25 points will cause the standard deviation to increase far more than the game in which he scored 15 points, because 25 is farther from the mean of 15.4. Thus increasing the spread of the data points. We now have the standard deviation of 5.7 points. But what does this number actually mean? It estimates that he has scored 15.4 plus or minus 5.7 points in 68% of the games that he has played. Let's say we didn't have all the data points, but we just had the mean and the standard deviation. Is there another way to visualize the spread in the data without using a histogram? I probably wouldn't be asking if the answer weren't yes. For this, we plot a Gaussian. A Gaussian is a curve that follows this equation. For the sake of the lab, we're going to think of the normalized Gaussian in the following way. The x value corresponding to the peak is going to be the mean of the data. So in this case, 15.4 along the x-axis is going to be our 1 along the y. Next, 1 standard deviation away from the mean, the frequency will drop to 60.6% of the maximum value. So it will receive a y value of 0.606 on either side of the mean. Similarly, 2 standard deviations away from the mean, the frequency will drop to 13.5% of the maximum value and will therefore receive a y value of 0.135. If we overlay the Gaussian with the histogram to compare the shapes, we see that the shape of the Gaussian kind of matches the shape of the histogram. It isn't exactly the ideal example of a normal distribution of data, because if it were, the shapes would be more aligned. One of the main issues is we only have 5 data points. We'll look at the histogram again once all the data from all 30 games has been added. But first, let's talk about the standard deviation of the mean. The standard deviation of the mean gives us a sense of the precision of the mean that we calculated. In other words, if we had chosen 5 other games at random, would we end up calculating the same exact mean? Chances are we wouldn't, but how much of a difference would there be? As you may suspect, the answer to this depends on the spread of your data, so it will depend on the standard deviation you calculated previously. It also depends on the number of data points you looked at to determine your mean. The more data you use, the less error there will be, so n must be in the denominator somewhere. The equation ends up being the standard deviation divided by the square root of n. The result estimates that if we calculated the mean of the points scored in 5 other games chosen at random, the mean would differ by plus or minus 2.5 points from the mean we calculated this time. Let's now look at the data from all 30 games. I don't trust myself with a calculator enough to attempt plugging 30 different data points into the equations previously given by hand, so I'm going to use Excel. Using the correct corresponding functions, I get that my mean will end up being 14.5 points per game, with a standard deviation of 5.7 points. As you can see, the histogram looks a lot more like a Gaussian now that we have more data points. So, using statistics, I can predict that there's a 68% chance that Tim Hardaway will score 14.5 plus or minus 5.7 points. And for the record, he ended up scoring 13 points on Sunday. So using statistics, we were able to accurately predict the number of points he ended up scoring.